What's up, everyone? In this video, we're going to be going over some circle proofs. So before we get into any examples, let's just do a refresher of our proof concept. So in these proofs, we're going to have triangle congruence involved, which, remember, there are 5 triangle congruence theorems, and these are the only justifications for proving 2 triangles congruent. So we have side, 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 angle, side, angle, side, angle, 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 side, HL congruent thoughts, right? Remember the song. And we know that once we prove that 2 triangles are congruent, the first thing that we should try to use right after is CP/CTC, which says, hey, if triangle 1 is triangle to triangle 2, then we know that all of their other corresponding parts are congruent as well. We also have triangle similarity. So for similarity, angle, which is AA, is like the most common used one for our course, but we also have side, angle, side, and side, side, side. But the difference here is whenever we have our sides, we're talking about them being proportional instead of them being congruent, okay? And then once you prove that 2 triangles are similar, we usually try to go ahead and use this concept right here where we say, hey, corresponding sides of similar triangles are in proportion. That's when you guys would really be doing something like, hey, A over B equals C over D or something, and then you cross multiply and you solve, right? And if you were trying to cross multiply and solve, the reason you would say is the product of the means equals the product of the extremes. So some other prior knowledge for us, when we're given parallel lines, we should look for our alternate interior angles, which are our z's, right? We should also look for corresponding angles, which are the F pattern. We want to look for vertical angles as well in our diagram. These are freebies, and we know that vertical angles are always congruent. We also want to look for the reflexive property. So this is if our triangles are sharing a side or an angle. So if we were sharing a side, it would kind of look something like this. And if we were sharing an angle, they would be like overlapping like such, right? And remember, when we're sharing a side, we put an X in. I'll draw this a little bit bigger. So if we have 2 triangles sharing a side, we always put an X in to mark that, hey, if we separated our 2 triangles, we know that those pieces would be congruent to one another, okay? And then again, right after proving triangle congruence, we should try to use CP/CTC. And then right after proving triangle similarity, we have to use the fact, or we should make proportions of sides, okay? Now, other circle properties to look for, so that's all prior knowledge. This is some new knowledge. So some common things, if you have a tangent line, you know we're creating a 90-degree angle with the radius, so we're going to have to mark that and justify that in our diagram as well. Inscribed angles that intercept the same arc are congruent. Inscribed angles that intercept half the circle must be 90 degrees. Now, the reason for that is if you have an inscribed angle just like this, we're intercepting half the circle, right? So this arc here would be 180. And then inscribed angles, we know, are half the arc measure, right? So that means that this would be 90. So that's kind of a visual justification for that property. And the other thing we should be using is the circle theorem cheat sheet. So every theorem that's popped up this unit is plausible to use. So you want to make sure that if you don't know them all, we got to start studying them. But we can use this document to help us for that. So let's get into our first example. So it says in circle O, EC is perpendicular to AB, and we want to prove that angle B is congruent to angle A. So just by taking a look at this diagram here, the first thing we should be asking ourselves is, are we proving similarity or are we proving congruence? Now, I'm going to mark what we're trying to prove. I'm going to erase it after, but we eventually want to prove that angle B is congruent to angle A, right? Now, by the looks of this, right, I feel like if we go backwards, we'll be able to use CP/CTC. Now, planning is very important, right? So if we take a look at this green triangle right here, or this turquoise triangle, and we take a look at our triangle that I'm highlighting in yellow, if we can prove that they are congruent, we can then use CP/CTC to say, hey, angle B is congruent to angle A. So that is going to be our plan. Our plan, we're going to choose congruence, and it's going to be for triangle DBC and for triangle DAC, right? So let's go ahead and make our statement and reason chart. Now first we want to write down our given. So we have EC is perpendicular to AB, given. So let's go ahead and label that. So if EC is perpendicular to AB, we know that we are going to have 90-degree angles here, right? Now, everything that we do should be helpful in getting these two triangles congruent, right? So we know that there are right angles on the other two sides as well, but those don't really help us prove anything about those two triangles. So right now, let's go ahead and say angle BDC and angle ADC are right angles. And because we know that because perpendicular lines form right angles. Now after this, we know that we have like our peanut butter and jelly statements. So once we have that two angles are right angles, we need to say that they're congruent. So angle BDC is congruent to angle ADC. And our reasoning there is because all right angles are congruent. All right. So another thing that I see about these two triangles is that they're kind of like glued together. They're sharing this side. They're sharing side DC here. So we want to put that as an X, right? Now that's also a dead giveaway that we're using the reflexive property. So we're going to say, hey, side DC is congruent to side DC because of the reflexive property. Now I think we're out of gas right now. I think we've used everything in our given. So now we need to see, is there a theorem that we can apply? And what's standing out to me is that we have these perpendicular chords, right? We have perpendicular chord EC and BA, and there's actually a theorem that talks about perpendicular chords, right? So if we go in our theorem cheat sheet, which is in your helpful hints folders, and we go to our chord theorems, there's a chord theorem over here that talks about when chords are perpendicular to one another. So it says a segment that is perpendicular to a chord must also bisect it. So from this, right, we know that if BA or AB is perpendicular to EC, we know that it's also going to bisect it. So we have our right angles formed here. Not only that, but we also know now that BD and DA are congruent. So BD is congruent to DA because when a chord is perpendicular, it also bisects the other chord, right? And again, this is just realizing that we had a theorem that we can use to help us make some conclusions. If you did not figure out this theorem, you really would not be able to move forward, right? Because now if you take a look at our triangles, now we're good to go. So now we can say that triangle DBC is congruent to triangle DAC. And if you take a look, we have side, angle, side, and we have side, angle, side. Now sometimes if you can't really see what's happening, you can separate your triangles here. At the top we have BDC, at the bottom we have here, right? So we have our X, we have our right angle, and then we have our congruent sides, right? So separately, if you take a look, you can really see we have side, angle, side, two congruent sides, and that congruent angle is right in between for both triangles, right? And then after we prove triangle congruence, we want to go ahead and use CPCTC. And from CPCTC, we already can say what we want to prove. So angle B is congruent to angle A because of CPCTC. Okay, so again, the whole idea is figuring out, is there a theorem that we can apply to give us an extra piece of information? Now let's go ahead and do another one. So in this example, we have in the diagram below, BOD is a diameter of the circle, so that's definitely going to be important. And we want to prove that ER times YD equals EY times RB. Now, plan similarity or congruence. Right away, this type of proof statement should be shouting out to you similarity, because we know that in order to get here before this, we need a proportion. And the only way to be able to make a proportion is to prove similarity. So we know we're proving similarity, but okay, which two triangles are we proving the similarity of? Well, let's go ahead and take a look at the sides. So ER and YD, if we highlight those, ER, YD, we also have EY, right, and RB. So we can see, like, those are 2 out of 3 sides of these smaller triangles over here. So we know that we're going to go ahead and prove the similarity of triangle ERB and triangle EYD. Okay? So now let's go ahead and get started. So we have statement, reason. Now, one, we have BOD is a diameter given. Okay. Now, the first thing that I'm seeing right now, I'm seeing inscribed angles. And remember that an inscribed angle has a vertex as a point on the circle, right? So, and if we take a look, right, if we take a look at this angle R right here, and let's highlight angle R in red. If we highlight angle R in red, and then we highlight angle Y in green, what you'll notice is that they're touching the exact same points on the circle. They're touching the endpoints of our diameter. Now, if we go to our inscribed angle theorems, which are over here, it says an inscribed angle that intercepts a semicircle is 90 degrees. And it says if it touches the diameter of the circle, right? So another way to think about this is when you have a diameter, that diameter is splitting the circle into two parts, right? So that means that this arc is going to be 180 degrees, which is half of the circle. So that means that both of those inscribed angles are going to be 90 degrees. They're going to be right angles, right? So 2, angle BRD and angle BYD are right angles. And your reasoning here could be worded a couple of different ways. I'm just going to word it in terms of the theorem. So we're going to say inscribed angles that intercept a semicircle are 90 degrees, okay? And then after we state that two angles are right angles, you guys know that we need to say that they're congruent. So angle BRD is congruent to angle BYD because all right angles are congruent, right? So now so far, we have this angle here being congruent to this angle here. And I also see some vertical angles involved. So we can take a look at angle BER, which is here, and then angle angle DEY, which is here. So for angle BER is congruent to angle DEY because vertical angles are congruent. And now we have enough. So remember, for similarity, the most common one we use is angle, and you need two angles in your triangle. So let's go ahead, let me clear the diagram so you guys can see what we're actually at right now. So far, we said that angle R is congruent to angle Y, right? We have our vertical angles here. So far we have angle. We're good to go for similarity. So we have triangle ERB is similar to triangle EYD because of angle similarity. And once we prove that two triangles are similar, we gotta make our proportions of our sides. So the first thing that I like to do is I'll just start off by using like process of elimination with my product here. So for step 6, I'm gonna start with ER, and I know ER is right here, right? So I'll put ER over, now I need to find the corresponding side of the other triangle. That's gonna be EY. So ER over EY. So we already used ER, we already used EY, equals, and then we have RB, which is here, over its corresponding side of YD, right? And your reason is when triangles are similar, corresponding sides are proportional. And then last but not least, you really cross multiply, but that cannot be your reason. So number 7, you're just going to restate this here. So ER times YD equals EY times RB. And your reason here is the product of the means equals product of extremes. So again, we saw our inscribed angles, right? We were able to use one of those inscribed angle theorems. We proved similarity, right? So first step, do you prove similarity or congruence? That's your first tackle. Figure out the triangles you need to prove it for. Get there first, and then pretty much after you prove like similarity, your next two steps are pretty much the same every time. And same thing for congruence. After you prove congruence, usually it's CP, CTC right after.